All right, so last section in this course, 5.10, we're going to talk about functions that are defined by integrals. And the main one we're going to look at is the logarithmic function. But there are other functions that are useful that we define with integrals. Um, and it may seem a little bit silly, I guess, to go back and talk about logarithmic functions because we've been talking about their derivatives and their integrals, right, all semester. But the way that we did it was a little bit shaky. It was a little bit hand wavy, and I'll explain why here in a second. But so the two major topics in this section are, first of all, we're going to provide rigorous definitions for natural log of x and e to the x. And then second of all, we're going to learn how to deal with integrals like this. Now, Fundamental Theorem of Calculus Part 2 tells us how to deal with the case when the lower limit of integration is a constant and the upper limit of integration is just x, right? But what do you do when you have functions of x in your lower and upper limits of integration? So we'll learn how to deal with that as well in this section. So as far as the first topic is concerned, right, providing rigorous definitions for natural log of x and e to the x. Earlier in the course, we defined the number e as the limit as x goes to 0 of 1 plus x to the 1 over x. Or equivalently, it's the limit as x approaches infinity of 1 plus 1 over x to the x, right? So we defined e to be that number, and then we said, okay, so if you have that number, that's just a constant, so then you can talk about raising it to the x power, and so you can talk about this function e to the x. And then we said, well, e to the x is 1-to-1 and continuous and all of this stuff, and so it must have an inverse. And so we said, well, we'll call the inverse the natural log of x. Okay? Those assumptions, right, they're reasonable assumptions, right? The assumptions that e to the x, is continuous and 1-to-1, those are reasonable assumptions, but they're not so easy to prove. And so we're going to take a slightly different approach. And we're actually going to work backwards in the sense that we're going to define the natural log first, okay? So another way to approach the natural log / exponential function is to define the natural log this way. We're going to define the natural log to be the integral from 1 to x of 1 over t dt. Okay? So in other words, we're going to define the natural log as this integral, right? So we just take that as the definition of what the natural log is. It's this integral here. And then we're going to define e to the x as the inverse of the natural log of x, right? So it's the opposite of our original approach. But this approach is nice because it allows us to prove the things that we simply took as assumptions when we used our original approach. And I'm not going to walk you through all of the proofs. You're welcome to look in your textbook on pages 326 to 331. They basically go through and they reprove all of the stuff that we know about natural logs. So they reprove all of the algebraic things, right? Like they reprove all of the derivative stuff and all of the integral stuff that we've learned about in the semester. But they do it taking this new approach. And again, what's nice about that is that it plants us more firmly on solid, rigorous mathematical grounds. Because for one thing, it allows us to prove that e to the x is actually continuous and differentiable and 1-to-1 and all of this stuff. So anyway, I'm not going to get into it too much, but what I will do is just show you one such proof. And this proof follows directly from the fundamental theorem of calculus. But basically we're saying the derivative of the natural log function is 1 over x, right? And so here's the proof, right? Derivative of ln of x. This would be the derivative of, well, we said we were gonna define ln of x with this integral, right? Integral from 1 to x of 1 over t dt. Well, by the fundamental theorem of calculus, this derivative is just 1 over x, right? And so you can prove, you can go through and kind of reprove all of the stuff that we know and love about natural log functions. Again, that's on, you can, if you're interested in seeing all those proofs, like if you want to see this proof, for example, that the natural log of a times c is the natural log of a plus the natural log of c, right? You can use this definition now to reprove this algebraic property. And so you can see these pages in the textbook if you're interested in looking at those proofs. So once we have the logarithmic function defined, and we can prove that it's one-to-one, and we can prove that it's continuous, right, using this definition, well, if it's one-to-one and continuous, then it has an inverse, right? And we take its inverse to be the function e to the x. It's still true. Facts like this are still true about the number e, right? And I'll show you some examples of that here in a second. But anyway, just for your information, logarithms aren't the only functions that we define by integrals. There are others. So a really common one is the error function. This one is used a lot in probability and statistics, but there's not a nice closed form for this integral, right? So you're not going to be able to get a closed form for this. We just express it in terms of the integral sign. So we call this thing the error function, and yeah, it's really common in probability. Another one is the Fresnel sine function. There's also a Fresnel cosine function, and these come up a lot in engineering. But again, there's not really a nice closed form for this integral. So there are lots of functions that we can define via integrals, and it's really a useful thing. Okay. So let me give you some examples of some things that we've talked about. So first of all, just to wrap our brains around the definition of the ln function that we've just given, let's sketch the curve y equals 1 over t, and shade a region whose area is ln of 3. Okay, so we're going to sketch the curve y equals 1 over t and shade a region whose area is the ln of 3. Okay, well, so first of all, the curve y equals 1 over t looks like this, right? So this is what the curve looks like. Now, if we want to shade in a region whose area is ln of 3, it might be useful to look back at that definition, right? So we said that ln of x is going to be the integral from 1 to x of 1 over t dt. And so therefore, ln of 3 would be the integral from 1 to 3 of 1 over t dt, right? So if we want an area, if we want a region whose area is natural log of 3, well, then this is the integral we're going for. Now, since this is the curve 1 over t, that means we want to find the area between 1 and 3. So if 1 is here and maybe 3 is there, right, then this would be a region whose area is the natural log of 3. So the area of that shaded region is ln of 3. Okay, and so that's just by definition, right? That's just by definition. Okay, here's another one. I'll let you pause the video and see if you can do this one. See if you can shade in a region whose area is negative natural log of 0.25. Okay. Now be careful. Okay, so natural log of 0.25, natural log of something less than 1 is a negative number. You make that negative and now it's a positive number. So this is still a positive area. But anyway, give the video a pause and see if you can figure that one out. Okay, so here's my solution. So there's 1 over t. I'm interested in an area of negative natural log of 0.25. Well, that's the same thing as ln of 0.25 to the negative 1 power, right? Just properties of logarithms. By the way, 0.25 is 1/4. 1/4 to the negative 1 would just be 4. So this is just ln of 4. So really I'm just looking for ln of 4, right? Well, ln of 4 is the integral from 1 to 4 of 1 over t dt. So there you go, right? So that area is negative ln of 0.25. Or in other words, positive ln of 4, right? Of course, that's not the only answer. I wonder. We must be able to go backwards, right, and get. Well, okay. So here's what I'm thinking. I'm not exactly sure how to express this, but if I'm thinking ln of 1/4, this would be the integral from 1 to 1/4 of 1 over t dt. And of course that is this limit of integration is smaller than this one. So if I switch them around and I go 1/4 to 1, I'm allowed to do that as long as I make this negative. And that's ln of 1/4. Well, okay, so if I want negative ln of 1/4, or in other words negative ln of 0.25, well then I can just multiply by a negative 1 on both sides. Negative, this becomes positive. And then I've got the integral from 1/4 to 1 of 1 over t dt. So there's another solution, right? That area would look like so if 1 is here, maybe 1/4 is like right there or something. 1/4 and 1, okay? So I obviously haven't drawn the figures to scale, right? I haven't drawn them perfectly well, but this area would be kind of skinny but tall. This area would be kind of short and wide, and they would be the same area, right? So this is also negative ln of 0.25. So that's another answer, right? Okay, so that's it for that one. Here's another thing just to sort of help us wrap our brains around the definition, this new definition for the natural log that we've been using. So given that ln of a is 3 and ln of c is 4, let's find the integral from 1 to ac of 1 over t dt. Okay. Well, we know that integral from 1 to x of 1 over t dt is just ln of x. And therefore, the integral from 1 to ac of 1 over t dt is just ln of ac. We also know that ln of ac is ln of a plus ln of c. And we also know, because we were given it here and here, that ln of a is 3 and that ln of c is 4. So we just get 7. Okay, so that's that. That's how this definition for the natural log function works. There are other things that we can do. For example, we could estimate, right? I'm not going to work this one out in detail, but we could estimate the value of natural log of 3 or natural log of 2 or whatever, right? And in order to do that, we would use the integral definition, right? We would say, well, I know that the natural log of 3 is the integral from 1 to 3 of 1 over t dt. And I know that now to estimate this, of course, to get the exact value, you would find an antiderivative, which is just ln t. Then you would plug in 3 and then plug in 1 and subtract them. ln 1 is 0. You just get ln 3. So ln 3 is the exact answer, right? But that requires us to know that the integral of 1 over t is natural log of t, right? But if we want, and also it doesn't help us to estimate this value, more importantly. It doesn't help us to know about how much ln of 3 is. But here's what we could do. We could say, well, I know that this integral is limit as n approaches infinity of the sum from k equals 1 to n of f of xk star times delta x, right? We can use that definition. And if we just wanted to, now if we're not going to take the limit as n goes to infinity, if we just want to get an approximation, we could say, well, forget limit as n goes to infinity. Let's just do this with a certain number of triangles, right? Like, or rectangles rather. Like, let's say, let's do it with 10 rectangles, right? And then you can use this to get a pretty good approximation, right? Anyway, so there are other things that we can do with this definition as well that are pretty handy and pretty nice. Let me move on though. So we can use that integral definition for ln of x to prove these formulas here. And again, the proofs of these are in the textbook, so you're welcome to read the proofs. But yeah, we can use the integral definition to prove these limits now, which is just something that we sort of took for granted. This should just be e, not e to the x. Anyway, so these are just things that we sort of took for granted, right, in the past. But we can use these facts to show some other things. So, for example, let's find the following limits. Let's do limit as x approaches positive infinity of 1 plus 3 over x to the x. Okay, so in order to do this, now we did stuff like this in the past, but I just want to remind you that one thing that you can do is you can change your variable here as long as you change them all accordingly. You can do basically like a u substitution, I guess, but for limits, okay? And what I need is I need this numerator to be 1, but I also need this number to be 1. So like one of the things that occurs to me is that I could maybe factor out a 3 and call this 1/3. The problem with that is then I'll have a 1/3 here, right? I'll have a 1 up here, which is good, but I'll have a 1/3 there, which is bad. I need a 1 here and a 1 there. So the way that I can achieve this is I can say let x equal, if I want this to be a 1, then I need a 3 down here. So if I call x 3u, then I'll have 3 over 3u, and the 3's will cancel. I'll get a 1 over u. So I'll have a 1 plus 1 over u, okay, which is nice. So so then this limit becomes this limit. X is now 3u. Okay. Now notice that as if 3 times u is going to infinity, well then u must be going to infinity, right? So I can drop the 3 there. So this is just the limit as u goes to infinity. And here the 3's cancel, so now I just have 1 plus 1 over u, which is exactly what I wanted. Now the only issue is that I have a 3u up here, and I need it to just be a u, right? In other words, the thing I'm going for is this second one here, right? I need it to look like 1 plus 1 over u to the u. But that's not terribly difficult at this point, because this is just the same thing as the limit as u goes to infinity of 1 plus 1 over u to the u. Actually, let me do it out here. Cubed, right? Okay, and that's nice because I know that this thing is just e, right? So this is just e cubed, right? So it's just e cubed. Okay, so that's the trick on these, is that you want to try to manipulate them. You want to try to manipulate whatever you're given so that it looks like this, or like this, or like this. So let me give you another example. And you don't always have to do a little u substitution thing, right? So, so let's do limit as x goes to 0 of 1 plus 10x to the 1 over x. Okay, so this one is looking more like this kind of definition, right? So we need it to be a 1 plus x to the 1 over x. We have a 1 plus 10x to the 1 over x. Again, I could try to factor out a 10, but then I'll end up with a 1/10 here, and that's bad because I need it to be a 1. I could do a u substitution thing again. I could let 10x equal u, right? So let u equal 10x. Or in other words, I guess that would mean that x is u divided by 10, right? Then what do I get? I have limit as x goes to 0 of 1 plus 10x to the 1 over x now becomes limit as u over 10 goes to 0 of 1 plus 10x is just u to the 1 over x is u over 10. 1 over u over 10. Okay, well, if u over 10 is going to 0, then u is definitely going to 0. So this is just limit as u goes to 0 of 1 plus u to the 1 over u over 10 would be 10 over u, right? Okay, well that's close to what I want. I don't want a 10 over u, I want a 1 over u. But again, I can think of this as 10 times 1 over u. Or better yet, I can think of it like this. It's 1 over u times 10, right? And so really that means that I can do that, right? And now this is just e, right? This is just e. So we get e to the 10th power. Okay. So that's that. And that's all I really want to say about this first item, this first topic, you know, giving rigorous definitions for ln of x and e to the x. The next main topic that I want to talk about is learning how to deal with things like this, where your limits of integration are functions of x. Okay. Fundamental theorem of calculus helps us, but there are some details that we need to work through. So, so here's the detail, right? So the derivative of the integral from a to some function of x, of f of t dt, Now, if this was just x, instead of being a function of x, if it was just a to x, well, then the derivative of this thing would just be f of x, right? But because this is a function of x, we actually end up having to use chain rule. And what you get is f of g of x times g prime of x, right? So you have to multiply by the derivative of that upper limit. And here's why. So let's say that capital F is an antiderivative for lowercase f. Or in other words, capital F is this integral here from a to x of f of t dt. If that's the case, then the derivative of this thing, well, using fundamental theorem of calculus part 1, this integral would be capital F of g of x minus capital F of a, right? But if we're taking the derivative, capital F of a is just a constant. It's going to be 0. And so the derivative of this thing is the same as the derivative of this thing. Okay? Now what's the derivative of this thing? Well, it's the derivative of the outer function times the derivative of the inner function, right? Chain rule. But capital F prime is just lowercase f. That's how we defined it, right? So capital F prime is just lowercase f. And that gives us the result we were looking for, right? So the moral of the story is fundamental theorem of calculus part 2 still applies, okay? We still just get f of, whatever this thing is, but we have to multiply by the derivative of this thing, right? Chain rule. So let me give you a couple examples of that, and then we'll be done with this section and therefore done with the course. Although you have a couple semesters of calculus ahead of you still, assuming that you're going to go on and finish the series. But let's evaluate some things. Okay, so let's evaluate the derivative of the integral from 1 to sine x of 1 minus t squared dt. Okay. Well, the derivative of this thing is, well, since you have a constant here as your lower limit of integration, then fundamental theorem of calculus applies. You can just plug this in for t. So we're going to get 1 minus sine squared x. Okay, but then you have to multiply that by the derivative of the upper limit of integration. So derivative of sine x is cosine x. And that's that. We could make this a little nicer, right? We know that 1 minus sine squared is just cosine squared. And then cosine squared times cosine is just cosine cubed. So it simplifies a little bit. But the main idea is this one, right? That you can still just plug in that upper limit of integration for t, and then multiply by the derivative of that upper limit of integration. So now the question becomes, what if it's not the upper limit of integration? What if it's the lower limit of integration? So let's calculate this thing. Let's find the derivative of the integral from ln of x to pi of dt over t to the 7th minus 8. Okay. So in order to do this one, in order to get it into the format where I can use fundamental theorem of calculus, I need this function of x to be up here as my upper limit of integration. So I'm just going to swap the limits of integration and make this thing negative, right? So I'm just going to say, all right, well, this is going to be derivative of negative integral from pi to ln of x. Now this negative sign can just be taken out of the entire derivative. So really you just end up with negative d dx. You don't have to show this much work when you do these problems, but you could just skip from this step to this one. Okay, but this is what we get. So now, the derivative of this integral, we can just plug in ln of x for t. So this is going to be 1 over ln of x to the 7th minus 8. And then we have to use chain rule, right? So we have to multiply by the derivative of ln of x, which is 1 over x. Okay? And that's that. That one doesn't simplify quite as nicely. I suppose you could distribute the x if you wanted to. So you could call this negative 1 over x times ln of x to the 7th minus 8x. I'm not sure that's all that much nicer, but either one of these answers would be acceptable. One thing that you should not do, though, is you should not say, right, ln of x to the 7th power is not the same thing as ln of x to the 7th power, right? So ln of x to the 7th power, that is the same thing as 7 times the ln of x. Okay, that's true. But ln of x to the 7th, the whole thing to the 7th, this is not the same thing as 7 ln of x. Okay? So just be careful with that. So that would be your final answer there. Now you could take this one step further and you could say, well, what if both limits of integration have some kind of function in them? So what if we're trying to find the derivative of the integral from, I don't know, x squared to x cubed of some crazy thing, right? E to the t squared dt, right? Something like that. So what do you do with that? Well, you can split this integral as follows. You can pick any number, and it doesn't even have to be a number between x squared and x cubed. You can just choose any number. Like, it really doesn't matter. I'm just going to do this randomly. I'm just going to choose any number. So I'm going to choose, say, let's go from x squared to, I don't know, 5. Oh, I shouldn't have closed that up, because then I need to add the integral from 5 to x cubed. Okay, that's how you deal with these situations. And then, of course, this one, you do the same trick that we did in part B. You switch the limits of integration, make it negative. So really this is going to be negative d dx of the integral from 5 to x squared of e to the t squared dt plus the integral from 5 to x cubed of e to the t squared dt. And, oh, sorry, I should have another differentiation there. Okay, so that's what this ends up being, and by now you can tell, okay, so I'm just going to plug in x squared for t, so I'm going to get x squared squared, that's x to the 4th, so this is going to be negative e to the x to the 4th, plus, and here I plug in x cubed squared would be x to the 6th, so I get plus e to the x to the 6th. And that's all there is to that. Oh, no it's not, because I have to use chain rule, don't I? Oh goodness. Well, let me try again. It's going to be negative e to the x to the 4th times the derivative of x squared, which is 2x, and then plus e to the x to the 6th times the derivative of x cubed, which is 3x squared. There you go. That's a little better. Anyway, so just rearranging a little, I guess you'd say it's 3x squared e to the x to the 6th minus 2x e to the x to the 4th. You could factor out some stuff or whatever, but there you go. There's your final answer. Okay, so that's that. That's all I wanted to say about that section. It's been a pleasure teaching this class.